and before I start the lesson, I just want everyone to know that I'm not a musician. I have never had any experience with anything musical. So I'm like, I know nothing. So I don't really know, I don't have any personal experience with most of the terminology in the lesson. Hopefully we have a couple of musicians in here. Anybody play an instrument or know a little bit of music stuff? Okay, good. So we're going to combine some of the stuff that I know about math, some of the stuff you know about music, and hopefully we'll all learn something new. Okay. So first, we're going to revisit a problem from last class. If the Earth's population was about 6 billion in 2000, and assuming the population doubles every 45 years, what do you think the population will be in 2090? 24 billion. It's going to double twice, right? Because there are two sets of 45 years between 2000 and 2090. So 2000 to 2090, that's 90 years, which is two sets of 45 years. And every time 45 years goes by, the population doubles. So the population is going to double twice. So I'm going to start with 6. I'm going to do times 2 times 2. Or I could do 6 times 2 squared. And that gives me 24 billion. All right, so why is 2090 easy, but 2120 would be hard? And in fact, we did 2120 last class, so let's skip. Let's do 2100. Why is 2090 easy, but 2100 would be hard? Yeah, so 45, there aren't an even number of sets of 45 in 100 years. So 2000 to 2100, there are 100 years. How many sets of 45 is that? A little bit over 2. It's somewhere between 2 and 3. So more than 2 sets of 45. So I have to double twice, but not quite 3 times. So we used the explicit formula for exponential growth that said the population at any year is equal to the initial population times 2, and then the exponent was the number of times we were going to double, right? So in the previous example, we had a 6. We said this was 6 times 2, and we were going to double twice, so we put a 2 there. So we're going to double however many sets of 45 are in 100. So if I do 100 divided by 45, 2.22 times, right? 2.22 times is the number of times I double. So I'm going to multiply by 2 that many times. So I'm going to use that as my exponent. So if I do 2 to the 2.22, and then times 6, I get 27.9966. Well, let's just go with 28. 28 billion. And then we should ask ourselves if this answer makes sense. For 2090, the population doubled twice and we got 24 million. So this is a little bit more than doubling twice. But doubling 3 times, what would the population be if I doubled 3 times? 48 billion. So this is bigger than doubling twice, but smaller than doubling 3 times. So this answer makes sense. So this is our general formula for problems that involve doubling time. how long it takes a population to double. You have an initial population, and you multiply it by 2, and then the number of times that you multiply by 2 is this exponent, and you calculate it by doing how much time's gone by divided by the doubling time. So that tells you how many sets of doubling time you have in the time that has passed. So we just did 2100, do 2400. See if you can predict the population of the Earth in the year 2400. Okay, so let's go over this together. From the year 2000 to the year 2400, how many years have gone by? 400 years. That's our elapsed time. Okay, then we have to figure out how many sets of 45 years have gone by, because we double every 45 years. So I do 400 divided by 45. 45 is what we call the doubling time, the amount of time it takes the population to double. So if I do 400 divided by 45, I get 8.89 sets of 45 years. Have passed. And that's the number of times I'm going to double. That's the number of times that I double. So my population in the 400 after 400 years, it's going to be my initial population, and then I'm going to double it a certain number of times. And I just calculated how many times I double it. So I did that by doing the elapsed time divided by the doubling time. And that came out to 8.89. So let's see what this is. 2 to the 8.89 times 6, 2,846.5. And that's billion people, right? So that's actually 2,846,000,000,000. I got the same answer, but... if it's just a rounding thing, you got. I put the 400 over 45. 888. So you're actually more accurate than I am, which is, yeah, I would definitely not take off for that. If it's just a rounding thing, I won't take off, as long as you're doing the procedure correctly. So this is trillions, billions, millions. So this is thousands. There we go. That's how many people. Okay, so sort of keep this in the back of your mind. We're going to talk about music for a few minutes. So math and the music scale. So sound is made of vibrations in the air that we perceive as sound through the hardware in our ears. Okay. So most musical sounds are made by vibrating a string or a reed or a column of air. And one quality of sound is pitch, how high or low the sound is. And a shorter string produces a higher pitch. So this is obvious if you've ever played a guitar or any other stringed instrument. As you move your finger down the string, thereby making the string shorter, the pitch goes up, the note gets higher. So the same phenomenon happens on a piano. If you look inside a piano, you see that the long strings are used for low notes, and the shorter strings down this end are used for high notes. So the frequency of a note is how many times the string used to create the note vibrates in a second. Okay, so we count how many times it moves back and forth in 1 second, and that's called its frequency. Okay. So its frequency is related to its pitch, because, well, we'll get there. Okay, so if you pluck a string at its full length, it vibrates at something known as its fundamental frequency. if you have the string, so you make the string half its original length and pluck it again, it produces the first harmonic. Okay? And having it again produces the second harmonic. So these are just vocab words associated with music things. If you don't know what they are, that's okay. The difference in pitch between the original tone and the first harmonic is called an octave. So if you have a string and you pluck it, it's going to vibrate at a certain speed and produce a certain pitch. If you cut the string in half, pluck it again, it's going to vibrate at a different speed and produce a higher pitch, 1 octave higher than the first. Okay, the difference between those two is called an octave. And then what our typical Western music scale does is it divides an octave into 12 tones, and that produces a scale. On the 12-tone scale, the separation between each tone is called a half step or a semitone. So this is these are the notes of a full 12-tone scale. So starting on a piano, you'd start at C, and this would be C, C sharp, and this one's D, and this is D sharp, and then those are just the names that we've given them. I don't really know the theory behind why we call them what we call them, but there are 12 tones. Now, if you were to sing a scale, like when you go do, re, mi, right? You always sing do and then do again at the end. You sing the next octave. So when you're doing that, you would sing, this would be do, re, mi, wait, no, doesn't matter. So anyways, if we went all the way to C, if we start at C and go to C, how many white keys are there in there? 8. 1, 2, 3, 4, 5, 6, 7, 8. If you sing the C that starts the next octave, right? There are 8. How many black keys are there? 5. What's special about 8 and 5? They're Fibonacci numbers, yeah. Which is actually not the point of today's lesson. It's just kind of a cool little thing I wanted to point out. So this is how our musical scale works. C and C are what we call 1 octave apart. And the string used to make middle C, this C here, would be half the length of the string used to make that C. There are other possible scales than the 12-tone scale. The Greeks used just the 7 white keys. Blues and jazz musicians use notes in between the notes of the 12-note scale. And non-Western music uses a variety of scales that are different from ours. All right, quick detour back to population growth, and then I'll link it after this. So suppose the Earth's population in the year 2000 is 260. Instead of 6 billion, we're just going to say it's 260. And that the population doubles every 12 years instead of every 45. What would the Earth's population be after 12 years? 520. We would just take the 260 and it would double 1 time, right? So that would come out to 520. If I wanted to find the Earth's population after 28 years, I need to figure out how many times I'm going to double, right? And the way I do that is I figure out how many sets of 12 there are in 28. So I do 28 divided by 12, and that's 2.33. So I'm going to start with 260, and I'm going to multiply it by 2, however many times I double, which is 2.33 times. So I'm going to do 2 to the 2.33 times 260, which is 1307.29. And then what if I wanted to figure out the population just after 1 year? Yes, divide the 1 by the 12. So this would be 260 times 2. I'm going to double it. And then I have to figure out how many times do I double it? Well, 1/12 of a time, right? Because we would double every 12 years and only 1 year has gone by. So I take my elapsed time of 1 divided by my doubling time of 12. That's what I'm going to raise 2 to, the 0.083. So I do 2 to the 0.083333, whatever. And then I multiply that by 260. 275.46. So this is how a population would grow if it started at 260 and doubled every 12 years. All right, so back to music. Doubling the frequency changes the note by an octave. So when you have a string, you have a string of a certain length, you pluck it, it vibrates at a certain frequency and produces a certain note. Then if you take that string and you cut it in half and pluck it again, it's going to vibrate at double the frequency. It's going to move twice as fast and produce a pitch 1 octave higher. Okay, so having the string creates a doubling the frequency, which increases the pitch of the note. Okay, so remembering that an octave is 12 half steps, we're going to use the exponential growth formula to model the frequency of the string. And we're going to use a doubling time of 12 half steps, okay, because every time we go 12 half steps, we're going to have the string is going to become halved and the frequency is going to double. So we're going to say the frequency doubles every 12 semitones. And we're going to start at middle C, which is 260 CPS as cycles per second. So we can also measure that in hertz. It's the same thing. So we're going to calculate the frequency of a note 1 octave above middle C, 12 half steps above middle C. So middle C is 260. As I increase in pitch, so I'm going to go above middle C, I'm going to increase in pitch, my frequency goes up. It doubles every time I go up by 12 half steps. So I'm going to double how many times? Once. So that gives me 520 cycles per second. That is the frequency of the note 1 octave above middle C. That's the speed at which a string will vibrate. So what if I want to find the frequency of a note that's 28 half steps above middle C? I'm going to start with 260, and it's going to double how many times? 2.33. We have 28 half steps, and it doubles every 12. So that's 2.33. Same problem that we solved before when it was representing population growth. And this came out to 1307, right? Cycles per second. And then if I want to find the frequency 1 half step higher than C, I would do 260 times 2 to the 1/12. So 0.0833. I'm going to 2 to that 1.05946. So this is 260 times 1.05946, which is about 275. So that would be the frequency of a note 1/2 step above middle C, which is C sharp. Yeah. And we increased it by a factor of 1.05946. We increased the frequency by a factor of 1.05946. That's what we multiplied the frequency of 260 by to get the frequency 1/2 step higher. So when I say factor, that means what did you multiply by? So the way we calculate frequency of a note is exactly the same way we calculate population growth when it's exponential. You figure out how many times it doubles. So I am going to start this activity with you about how we design a guitar, how a guitar is designed. So if you measure the length of the string of a guitar from the nut to the bridge, then the nut is that small white piece of plastic right here. This is the nut. And then the bridge is right down here, where the strings end. So you measure the length of string from the nut to the bridge. And I didn't bring a guitar in, so we're just going to say that that is I didn't write it down on here. I thought I wrote it down. I think, what's a normal length of a string? Like 26 inches? 1 foot?
That's a ukulele, not a guitar.
Yeah, I think 26 inches would be a good one. 24? Okay. So let's say, and I actually think it varies from guitar to guitar, because some guitars are larger than others. So it could be 24, could be 26. We'll just make one up and use it. Okay. All right, so to increase the frequency by a factor of 1.05946, that is to go up 1/2 step, we have to shorten the string, right? So we have to, this activity is going to help us figure out where you put the frets, right? So these little lines on a guitar are called the frets, and those are where you push down to make the string effectively shorter than its fundamental length. And when you push down on those, you make them shorter by a certain amount, which changes the pitch by a certain amount. So we want to figure out, where do you put these frets in order to create our 12-tone scale? So if you want to increase the pitch by 1/2 step, you multiply the frequency by 1.05946, which means you have to shorten the string by that same factor. So you're going to take the string length and divide by 1.05946. That would shorten the string by the same factor. You want to increase the frequency. Okay, so I'm going to take my 24 inches and divide by 1.05946, and I get 22.65 inches about. So if I want to, if my 24-inch string produces a certain note, to increase the pitch of that note by 1/2 step, I would want to pluck a string that's 22.65 inches. Right? I did that by doing 24 divided by 22.65 inches is the length of string that will produce a tone 1/2 step higher than a 24-inch string. So if that's the length of string I need plucked to create the note I want, where should I put the first fret? What's the distance from the nut to the first fret? Yeah, somebody said it. So let's go back to the picture. I wish this was smaller. Maybe I can make it smaller. Okay, so if the distance from the nut to the bridge is 24 inches, that produces some certain note. If I want to shorten that string to 22.65 inches in order to produce a note 1/2 step higher. So this first fret should create a string that's 22.65 inches, which means that the distance from the bridge to the first fret would be the difference between those two numbers. 24 minus 22.65, which is 1.35 inches. So from the nut to the first fret, I would do 24 minus 22.65, 1.35 inches. All right, now I want to raise the pitch another 1/2 step. Question or just stretching? Okay. So if I want to raise the pitch another 1/2 step, I'm going to take the previous length and divide it by 1.05946. So that's how you raise a 1/2 step. Divide. To find the length of string you need to raise the pitch a 1/2 step, divide by 1.05946. I'm going to do 22.65 divided by 1.05946. So I get 21.38 approximately. So what should the distance between the first and the second fret be? Say it again. 1.27 inches. And we got that by calculating 22.65 minus 21.38. So yeah, I heard some people just saying this is a recursive process. Totally, it is. You're taking your previous length, dividing by 1.05946 to get the next length. So this is how we design a guitar. This is how you figure out where to put the frets in a guitar. Because if you've ever looked at a guitar, the frets are not equally spaced, right? Frets aren't equally spaced. This is how we figure out where to put them. So in your groups, I want you to finish the rest of these calculations. Finish designing your guitar.